Hello. Okay. Continuing on from last time. So last time we reorganized the forward and backwards propagation. We rewrote a whole bunch of the fundamental stuff of our framework so that more stuff is part of the layer. The layer is in charge of its own forwards and backwards propagation. And it just returns a bucket of parameters in the backwards prop. In the forwards prop, it just does the computation that brings the vector forwards. In the backwards prop, it returns a bucket of parameters, gradients. So each of these is gradients of different parameters. Delta is required because that's the gradient that flows backwards into the layers that come before it. And if you add any other gradients, then those just become other learnable parameters of this layer. So we changed it so that we've got linear layers, which is a thing that has weights and biases. We have ReLU layers, which is now just a function, an activation function. It doesn't have its own weights and biases, so you can pair it with a linear layer. You can put it after a linear layer to recreate what we used to call a ReLU layer in our old framework. Softmax is the same. Softmax now has no weights and biases. It just applies a softmax function. And we added skip layers. These were complicated to implement, but we don't have to think about them anymore. Ideally, now we can stop thinking about the implementation of them and just think of the simple thing that they're doing, which is, well, I'm trying to think. I might actually, why don't we do this just to simplify the thing, because the skip layer is doing two things. The first thing is it has a bunch of internal layers. So this is how it looks like when you're using it. It has a bunch of layers internally, and then it takes the input to the whole thing and it adds it to the output of the whole thing. So our forward and backward look really complicated, but all the complicated stuff is just the fact that it has to deal with internal layers. So I want to split off the internal stuff. Just call this block. Move all of the implementation of skip into block. And then I'm just going to add back forward and backward. This is going to inherit from block. Add back forward and backward. Block is not going to do the adding here. So it's just going to do X when you go forward, and when you go backwards, it's not going to add the gradient back. So it's just going to do this. Then skip is going to call super dot forward. Which passes X in. So you just return, I can just do this even. One line. Forward is you add X to the output of the block stuff. Backward is similar. You call super.backward DA. Grads is going to be equal to that. And then we're just adding D back to grads. So now it's obvious what skip is doing. It's when you go forward, you add the input back to the output. When you go backwards, you add the delta from the end to the delta from the beginning. Okay. So goals for today, we broke saving and loading. We haven't implemented that for the skip layers yet because they have their own internal layers that need to be saved and loaded also. So we're going to implement save and load for skip layers. And then we're going to implement LayerNorm, which is these green blocks in the transformer model. And I'll talk more about what it is and what it's for once we get there. So let's start with saving and loading. Oh, also in between streams, I trained this model. One thing I learned is that you should put the ReLUs outside of the skips. Trying to remember the reason. Like this last ReLU, before I had it like this, but it's better to have it on the outside. I think that's because you know what? I don't know. I actually don't know. I was thinking of it like if these were sigmoids, it would make sense to me. It's because this thing could become large and then the sigmoid brings it back to being small. Whereas if you did the sigmoid inside here, you'd be adding, like your output wouldn't follow the sigmoid statistics anymore because you're adding whatever the input was back to the output. So there's something in there that kind of makes sense to me intuitively, but I don't know how to explain it in a way that could make sense to anyone else. But it seems to work better, and I read something online where someone said make sure you put your activation functions outside the skips, and also it looks like that's what's, like if you look at this picture here, from the, I think this is from the original, from the original ResNet paper. They do the ReLU after the add. So that's what I changed it to do. And then I trained this network, which is pretty deep, like 1, 2, 3, 4, 5, 6 layers. Pretty deep for the types of networks we've been doing. It learns pretty quick. So this is 20 characters here. So already at almost 49% after the first epoch. It's pretty slow, so I only let it run for 6 epochs, and that still took an hour and a half. And then let's take a look at the output. So scroll all the way down. Let's say hello. Hey, pooks like us, the Ulanet, wants the G a reactor. Re a lane flad. In Sephiroth, Slore 2, you at wrong, you get ting image to per. Barrett, that's that sow, something no that you talk. Cloud, ... BM ... Sephiroth, Shinra use you want to get now your gore. So it's pretty interesting. It's like it didn't memorize the text like it did before. I did actually, now that I look at it, I ramped up the regularization really high, so it would be really hard for it to memorize the text. But if you look at it and like blur your eyes, it looks really good in the sense that like it's following a lot of rules of language and English. Like capital letters after periods. When it makes up words that are English-like. Wargenever, Ulanit, G, so, or I guess so is a word. Newtledge, Lateria. So there's some good stuff and some bad stuff here, but it's cool that we were even able to get to 52% with such a deep network. Anyway, let's kill this, and we can't save it because we haven't implemented saving yet. So let's do that now. Save. So right now, the way I'm saving is for each layer. No, first I'm saving the type of each layer. Then I'm saving each layer. And then when I load, first I load the type of each layer. Then I use that type to load the layer. So yeah. And that works, but it's not going to work for this block layer because, so save kind of makes sense. You just say for each layer, save the layer. Load is not going to work because I also need to know the types of the layers. So I guess actually I can just do the same trick, save the types of each layers. So if I go to network, I could actually just copy this, go to layer, do the exact same thing. This is for save. And then in load, I could do the same thing, I think. So load the classes. I don't have a net.layers. Instead, I have a CLS. What am I trying to say here? I want to instantiate a layer of my class without passing in any layers, and then set the layers myself. So I'll call this layer equals this, layer.layers is that, and then return layer. This is supposed to return a layer. This is supposed to return none. So load should return a layer. So I suppose Relu should also be able to load itself by just returning an instance of itself like that. This should be the I'll just do that. This should be what the ones that don't have any particular loading behavior do. Because we still need to return an instance. So you're doing it. You're a subclass of block. Okay. Okay, so if that worked, then we've implemented saving and loading. Let's see. So let's make a much smaller network. All of these should just be 80. Let's change cars to just be 10. And let's train a network real quick. And it's broken. How did I break it? Oh, I just forgot to change this to 80. This is why I don't like this format. Maybe we'll change this to have something that comes before, something that parses your definition and adds the right dimensions to things. Because I liked before when I could just say input is this many, the first linear layer is this many. And I didn't have to make sure that they matched in between. So it doesn't need to train very long. If it is not able to finish a single epoch in a few more seconds, I'll just kill it and we'll just use a not well-trained example. Okay, it's finishing its first epoch. 46%. Let's kill that. Try a prompt. So if you say hello, it says Shinra Nodo. Okay. So now we kill this, save the network as skip. Can't pickle. Okay. What's the issue? Network.py line 21. Can't pickle class generator. Oh. Yeah, I wrote that wrong. So let's go here. I meant to save a list. So I think I meant to close the parenthesis here and do it like that. And I probably made the same mistake in here. Yeah. Okay, let's try that again. I think the other thing I should do is okay, let's stop this, say hello. So it says thing, Walor and it tor rim. So now we'll kill this, we'll call it skip, save it, and now we'll try to load it, skip. Can only convert an array of size 1 to a Python scalar. Okay. Dot item. Where is it? It's over here. Dot item. So it doesn't think I'm supposed to say item here, which is fine as long as I can iterate over it. Okay, now the same error happens over here. Right here. Say hello. It's not the same output. but it's close. Huh. What does that mean? Hello, hey, the what's you Rotga. Kill that, load it again. Hello. Hey, the what's you Rotga. Oh, I have an idea. So I wonder if it's because we're setting the random seed at the top instead of after each prompt. Because if I said hello again, I'll probably get a different answer now. Yeah. So what if I reset the seed after each prompt? Then would I get the same answer every time? Hello? Hey, the what's you Rotg? Hello? Hey, the what's you Rotg? Okay, now I get the same answer every time. So let's try this one more time. We'll train it from scratch. What was the other thing I was saying? Oh, I think I'll change layer from being a protocol to being an abstract base class so that I can implement the default init save and load. I don't remember all the differences between protocols and abstract base classes. Okay, so let's stop it here. Give it a hello. I little hookiver. Kill it, save it as skip, load skip. Hello. I little hookiver. Good. Saving and loading is working. Clear. So one of the annoying things here is that I'm redefining these methods a bunch when I don't need to. Whatever, it's fine. We'll just leave it. I guess I have block here. I could have like activation function as its own layer if I wanted to. So I would just say activation function. That only implements these things. Relu subclass is activation function, which means it doesn't need to worry about these. Softmax is the same. You don't need these. Skip is a subclass of block, so it doesn't need to implement that stuff either. And linear needs to implement everything because it has internal variables and stuff. All right. So the other cool thing is now I could try having block here. Block, Let's add a no QA so it doesn't remove our import. And this should work, but it should, without loading. This should work, but it should learn more slowly because it's not gonna have a solution to the vanishing gradient problem the same way that it did when we were using skip. So this should basically be the same as this. So let's see if it does. We were getting to around 46% on the first epoch. If I'm right, we'll get a little bit less than that on the first epoch without the skip layers. Okay. I can remove this comment now. Oops. Yeah, a little less than before. Not much less, 0.5% less. So let's kill that. Add the skip layers back in. And let's now move on. So we accomplished this. We fixed saving and loading. So now we get to do LayerNorm. So if we take a look at the transformer architecture, we've got these norms all over the place. My understanding of norm is that, it means normalize, and the intuition for it is that you should do it before sending your input into some type of layer. So you can see in these blocks, it usually comes at the beginning. I don't actually know why we normalize. I guess because this is some layer, the linear layer out here. Is that what it looks like? In this diagram, they have the norms coming at the end. Okay, so again, I don't know anything about machine learning. I'm learning all of this stuff in real time. I don't know how any of the stuff in the transformer works that isn't something that we've implemented so far. So we're figuring it out together. My understanding of norm is it's helpful to normalize inputs before sending it into a neural network, because that helps the neural network learn, because you don't end up with some of the numbers being huge. So you're kind of balancing the size of all of the numbers to have a fixed standard deviation and mean. So that the neural network can better use the information without having to worry about some of the numbers blowing up, and now it needs the weights to be like super tiny for those ones but not for other ones. That's my understanding, is that it's helpful to make the weights and the biases all be around the same size. It helps the network learn by normalizing the input before you send it into stuff. So that's why there's norms all over the place in the transformer architecture. So the norm that people use in transformers is called a LayerNorm. LayerNorm. Let's just look it up. Normalization layer layer normalization. Layer here. So LayerNorm normalizes across all the features within a single data sample. It is a key component of the transformer model. So it's defined by you take the input x, you subtract mu from it, you divide it by square root of sigma squared plus epsilon. Mu and epsilon are the mean and the standard deviation. Or sorry, mu and sigma are the mean and the standard deviation. Yes, mean is mu, variance is sigma squared. I think variance is the square of standard deviation. I could be wrong about that. You add epsilon, and the only reason to add epsilon is so that you're not dividing by 0. So you just add some little number that you know is positive. And then you take this whole thing. This would be enough. What I've read is that this would be a layer norm. But LayerNorm works better if instead of just setting an absolute mean and standard deviation, you let the network learn what's the best mean and standard deviation to set it to. So that's why you add beta and multiply by gamma, so that, and then beta and gamma are learnable parameters. So instead of me looking at the network and saying, I bet it would work well with a mean of 0 and a standard deviation of 1, which would work. Like that would be a layer norm, and it would help. If a layer norm would help, then that would help. But it works even better if the network can choose its own mean and standard deviation. So let's do it. Let's add why don't we add a layer norm just right in the middle here? Layer norm. Does it care about its size? Yes, it does, right? Because the beta and the gamma need to be a certain size. Well, no, are they just numbers? Beta and gamma might just be numbers. I think I saw a different definition of a layer norm that included a matrix that's learnable, but maybe I'm mixing it up with one of the other types of norms. It looks like beta and gamma are just a number, which means layer norm shouldn't care about what dimension it is. Okay, so we'll do that. We'll add layer norm as a new type of layer. Layer norm is, it's going to be like linear in that we have to define all of the parts of it ourselves. So I'll copy linear, add right below it. To do. We don't need any initializers, I think. We do have to set, these are gamma and beta. Gamma, beta. How How about 1 and 0 to start? So we've got gamma is 1, beta, or float. When you save, you're going to save gamma and beta. When you load, you're going to load gamma and beta. Okay. Oh, can't call this linear, got to call this LayerNorm. It's funny, it has layer in the name. All right, and then the forward is kind of straightforward because we're just doing this formula. So x hat equals x minus mu divided by, and we'll do a numpy square root of sigma squared plus epsilon. Yes. And then we just return gamma times x hat plus beta. Oh, hold on a second. These have subscripts, so these are vectors. So this is not a float. This is np.nd array, np.nd array. Gamma is np.ones, and we do need a size. Size, which is an int size. np.zeros size, and it's size comma 1. And maybe this I think this might need to be a tuple. Okay. Self.gamma, self.beta. Epsilon is going to be equal to some small number. Mu is equal to something, sigma is equal to something. So mu is the standard deviation. Numpy mu is the mean. Numpy.mean x. And now we have to remember that whenever we're doing the forward pass, we're passing in a whole mini batch at once. So this would be the mean along the vertical axis. And I never can remember which axis is which in NumPy axis. Zero is the direction along the rows. 1 is the direction along the columns. So this would be 1. And sigma is the standard deviation of x along the same axis. Okay, we're getting somewhere. Oh, wait, this is the square of the standard deviation. Does NumPy have variance? var, numpy.var. Does that mean variance? NumPy variance. NumPy.var, okay. So sigma squared is the variance, which means numpy.var x axis equals 1. Okay, so that's the forward pass. Wait, let's... So... Hold on. X is a matrix. So we actually have to do that same trick as before. No, wait. I guess I want to subtract mu to each value in each column of X. Is that what it does though? Python import numpy as np, np.array 12, comma 34. So a equals this. I forgot the outer. Okay, so we've got this matrix. B is going to be np.array 5, 5. We've got this. Now if I do A minus B, hold on. Let's say B is 5, 1. A minus B. So did we subtract 5 from both of these? Yes. And 1 from both of these? Yes. Okay, so this is what I want. It's weird to do operations on matrices that are not the same size. And then sigma is going to be a different standard deviation for each row, for each column, I mean. We're going to add epsilon to all of those. And then we're going to take the square root of this vector. NumPy dot square root of b is something, b plus 0.01. Okay, and then if we divide a by b, by that I mean, we've divided the left side by 5-ish, or by, I guess it should be by 2.2. 3 divided by 2.2 is 1.3, and the right side by 1.005. So 4 divided by, okay. Okay, so this is the right expression. All right, backwards. So this is a lot harder, and I'm not so good at the chain rule, because the way you would do this is you'd want to figure out, so first of all, I need to figure out delta, I need to figure out my learnable parameters, so gamma, and beta. And so you have to find the derivatives of things of the loss function with respect to these things. And I'm not so good at doing that, so I asked my friend Gemini to help. Yes, Gemini. And so we're going to be using some AI to do this, the calculus to go backwards. I feel like this is cheating a little bit, but it's also been helpful to be able to make progress. Like now I'm able to read this kind of stuff and understand it. So maybe by the end of this, I'll be able to do this kind of derivation myself. But right now, I need help from AI. So the forward pass, this is what we've done already. The backwards pass is here. So we've got the gradient with respect to beta, gradient with respect to gamma, gradient with respect to the input. So that's delta. The gradient with respect to the bias is equal to the gradient with respect to the output, which is delta. So this is D, I think. Or it's not delta of this layer, it's delta of the last layer. So I think dl by dy for us is D. So one weird thing is that this vector is not the right size, right? This vector is going to be a column, and this vector is going to be a row. Or no, I guess it'll be a column. Yeah, okay. So I think this is right. Okay, the next one is gradient with respect to gamma is D times z hat. Z hat is the normalized input. So that's what we called x hat. So if our gamma should be D times x hat. Self.cache equals x hat. I don't know what else we'll need, but we'll at least need that. X hat equals self.cache. Okay, so now we've got our gamma and our beta. And now the z, so this is the more complicated one. So delta equals 1 over s, and s is the standard deviation. So square root of this thing. So let's cache this. Standard deviation equals this. Cache the standard deviation. So we grab it in the backwards pass. Delta is 1 over this times dl by dz hat which is d times gamma. So dl dz hat equals d times gamma. Do I have gamma? Gamma is my what do you call it, a learned parameter. So I have it on self. dl dz hat is this. So you are this times, oops, dl dz hat minus 1 over n. What's n? N is what is n? Is that explained somewhere? The number of elements in the vector. The layer size. Okay, so that was the thing I was trying not to have to know. I can figure it out from A. So that's going to be the number of columns of A. So A dot shape of 1, I think. If you have an n by m matrix, m is the number of n by m matrix. Which one is columns? M is columns. Okay, so this is right. So this is minus 1 over n times something, let's come back to that, minus z hat over n. What's z hat again? Z hat is the normalized input. What does that mean? Oh, okay. Z hat is x hat. So, wait, why did I think I had x hat? Oh, I had it for a different thing. Okay. So, this is something minus x hat over n times something else. What is this term? This is the sum of the derivatives of L with respect to z hat. So that's already what this is, standard deviation dl dz hat. This is sum up the columns. So here you do np.sum dl dz hat axis equals 1. And then this is the same thing, but then you multiply by z hat. Is that the right way to say that? I don't know if that's the right way to say that, because the subscript here is zj. So I don't think I can just take the z out and turn this into a z hat squared. Um, so this is it's a little hard to think about because this is treating the z's like they're vectors, but for me they're matrices because I'm doing a whole batch at a time. Couldn't I take this z out and just do z squared out here if it were a vector? I'm not sure why I couldn't do that, but it's hard to. I'm not so good at linear algebra that I can figure that out in my head. So if I were going to do this manually, or what am I doing here? I'm making, so Z is a matrix. No, let's think of it as a vector and then we'll extend it to a matrix. So what would happen with a vector? Z Z1, Z2, Z3. DZ1 so you would have this would be like a component wise multiplication, and then you take the sum, so you'd multiply these things and then you'd sum everything at the end. So this is a Hadamard product. This is sum of dz Hadamard product z is what this is. And I think that that's the same even when it's a matrix. So I think I can just here say times sum, and I have too many parentheses here. I don't need this one. np dot sum dl dz hat Hadamard product z hat, or I call it x hat, axis equals 1. I have the I have the feeling that I can just square the x hat and that I'm doing something redundant here, but let's leave it at that for now. Let's rename some stuff so that it's consistent. So let's not use the letter Z. Let's use the letter X so that everything is consistent. Yeah, that would be what this delta is. Okay. Now, it's going to be really hard to tell if this is working. Because I don't know if I don't know how well this is supposed to do, even if it were working, to put a layer norm right in the middle of the network like that. Oh, I thought I decided you don't need size. No, I guess you do need size for the beta and the gamma. So if we need size, then n here should just be self.size. This should be 80. Okay, where is that? X minus mu divided by standard deviation. Well, first of all, I should be more careful there with the operator precedence. X minus mu should be in parentheses. I don't think that's the issue, but let's at least make that be correct first. Okay, so you can't do x minus mu, even though I thought I tested that. So I would like reshape to be I don't know how to say this. It's like by 1. I guess x dot shape of 0, comma 1. Is there a better way to say that? NumPy axis reshape. I think PyTorch calls this squeeze and unsqueeze. But I'm not sure. Three becomes 3, comma 1. Wait, I don't know how to read this example. Why is it like not taking up the right size? Okay. I don't think this is what I'm looking for. Whatever, this will work, I just hate it. NumPy axis dropped the 1. I don't know how to search for this. Maybe I do want to unsqueeze. The equivalent of unsqueeze is expand dims. So I don't know. I just want a 1. Is that what expand dims does? Why don't we just try it? NumPy or Python import NumPy as np np.array 123 a equals this, a.shape is 3 comma nothing, a dot expand dims. How do you do it? np.expand dims a axis equals 0 dot shape axis equals 1. This is what I want, but this is not better than just saying reshape this comma this. Oh, is that what keep dims does? I think I finally understand the point of keep dims. So now you should, hopefully won't have to reshape. Let's see. That's fair, actually. So why don't we go back to doing this the way we were doing it before. A dot shape of 1. Keep dims. Keep dims. Always keep the dims. Okay. So my gamma and my beta don't have the same dimensions as my gamma and my beta. Which one is causing problems? Well, why don't we try to figure it out? So these will be 80 by 1, 80 by 1. I think I need to do a sum here. np.sum. I did the same thing for bias, right? Yeah. And here, instead of this reshape, I probably could have done keep dims. I'm learning now. So np.sum, np.sum. Well, this one's probably right already, because D should just be a vector. This one needs to be summed along the rows. So that would be axis 0. Keep dims true. Okay, let's figure out which thing it has an issue with. So network, this has been fixed. Don't need that to do anymore. Print key. It has a problem with gamma. But if I'm summing across the dimension, how did it end up? Maybe we don't want keep dims in this case. How did it end up being 80 by 50? Also, I think I have the wrong. If this is 80 comma 50, I want 80. I don't want 50 for this n. All right, so it's telling me that this is wrong, right? It's so print d gamma dot shape. And is that going to say 80 by 50? $50 comma nothing. That's curious. Do I have the wrong axis? NumPy axis. Well, actually, there's a different problem here. This is a matrix. This is a vector. And I'm doing a Hadamard product. Is that what I mean to do? Let's take a look at the thing that I want here. So if z were a vector, I would want to multiply the components of d, which is dl dy, by, so this would be a Hadamard product between the components of dl dy and the components of x hat. So if x is a matrix, it's the same thing. I still want to just multiply. I don't want to do a matrix multiplication. So this seems right. And then I want to sum the columns so that I end up with just one column at the end. So this should be 80 by 1. I guess you're telling me that's supposed to be axis 1? No. Because now I end up with 80, 80. No, it was 80 nothing, which is right. It's just that I also need a keep dims equals true. Oh, but now it should go back to 1, I guess. I don't know why this is 1 and these are 1 though, because these ones I wanted to sum the other way. What is going on? Now it is 80, 1. So what's 80, 50? Oh, now it's the beta. Okay, we fixed the gamma. Beta. I think this is the same thing. So without the times x hat. Okay, it's doing stuff, so let's stop printing. The thing, I'm just confused here because these these should be the opposite axis as the one below. So does this still work? It works. And these also, these should be along this axis. This should be along the 80 axis, not along the 50 axis. So, okay, so let's remove the prints. Let it run for a minute and see if we end up with anything. The only way we would know for sure that it's working is if it gives us a better network than before, so better than 45%. If it's less than that, then it's hard to know if it's not working or if it's working, but putting a LayerNorm in the middle of the network doesn't help. So that's a problem with what we're doing. It's hard to know if it worked. I'm especially concerned that putting either axis seemed to not cause it to crash. I was hoping to rely on crashes, dimension mismatches if I screwed up my axes. 16%. Okay. I mean, that's not good. Because that means it's able to learn something, because it would be 1% if it were not able to learn anything. but we severely handicapped it by adding the layer norm. So that's the scenario where I don't know if the problem is adding the norm, or if the problem is that the norm's not working. See, it learned something. Okay, let's kill this. Layer norm example. Images. I just want to know that this is just highlighting where they are in the transformer network. So if I put a norm as the first thing, surely that's not supposed to cause a lot of problems, because the point of norms is to put them in front of things. Oh, okay. It causes the problem. It caused a problem right away with overflows. So let's kill that. I don't know. Here they're putting a layer norm right at the end without a ReLU here. 80. This one right here. So I'm thinking putting a norm before a linear softmax. It can't be bad because that's what happens at the end of a transformer. It goes norm linear softmax. It goes add norm linear softmax, and we're doing add norm linear softmax. So if this gives something a lot lower than 45%, I think we can be confident enough that the problem is with the implementation. Yeah. Okay. It's just going to be hard to figure out. But let's just go through one at a time and see if we've implemented it correctly. It's also possible that Gemini has misled us, and that we're not going to be able to figure out today, if that's the issue. Okay, mean. Along the feature axis, which should be 0. Why don't we confirm that? Python import numpy as np. So actually, let's exit. Let's print mu.shape. 1 comma 50. That makes sense, because for each of the 50 samples, we're calculating the mean of that sample, the mean of the features in that sample. So we should have, if there were just one sample, we would expect mu to just be a number. So 1 by 50. Variance should be the same. It should be 1 by 50. So sigma. Or, yeah, sigma. One by 50, good. Okay. Standard deviation is this bottom thing, square root of sigma squared plus epsilon. Do people use a specific value of epsilon? LayerNorm epsilon. So this looks the same as what we're doing. Epsilon. They don't say. Default. E to the -5, so that's about this. I don't know if this is -4 or -5, but it's one of those. So you get x hat, and then you multiply this whole thing by gamma. Okay. Gamma is a vector, beta is a vector. They should both be 80 by 1. So let's print gamma.shape, self.beta.shape. $80 by 1. Okay. That's expected. Then for the backwards pass, we grab the x hat and standard deviation from the forwards pass. We're not using the activation. I wonder if it should be expected or not. So gradient with respect to bias is gradient with respect to the output, gradient with respect to the activation. So that's what D is. Gradient with respect to gamma is D times x hat. And then I'm taking the sum along the sample axis because I'm doing multiple at once. Okay. So this looks right. I double checked this a few times, but let's check it again. Loss, derivative of the loss with respect to the output, that's what I call D. Now that's what I call D. Times x hat. And if this were a vector, so if we were just doing it for 1, you would take you would just do D Hadamard product x hat. Okay. We're doing it for a matrix, so but we still do D Hadamard product x hat, and then we just sum along the sample axis. And then delta. Delta uses this intermediate gradient. So dl dx hat, which is equal to D Hadamard product gamma. Now D for me is a matrix. So I'm still, and x hat is also a matrix for me. I'm still doing the Hadamard product, but my dl dx hat is a matrix and theirs is a vector. So standard deviation here is a vector. And I'm dividing this thing by that vector, which is a little weird. But I guess it's just a Hadamard product. So we've got the 3 terms. dl dx hat, which for me is a matrix, minus 1 over n. N is the number of features, so that's shape of 0. Let's just confirm that. This should say 80. Right? Yeah, it should say 80. Okay, n is 80. 1 over n times sum of the features, sum along the feature axis, so that's what this is, of dldx hat. So this is just a number in this equation. In this equation, it's a vector, 1 by 50. X hat is a matrix. Print x hat dot shape. It should be 80 by 50. Okay. This is a matrix. If you just do divide, I think that's Hadamard division. So divide that by n times this, which is a sum along the feature axis of dl dx hat Hadamard product x hat. That's what it would be if it were a vector. And that's this if x hat were a vector. And so it's the same when x hat is a matrix and dl dx hat is a matrix. Yeah. And then you take the sum along the feature axis. Okay, so I did this. It looks like I did it right, as far as I can tell, after double checking. So gamma and beta are 80 by 1? Yeah, they must be. Yeah, they're both 80 by 1. So it looks right to me. Z is the input, right? Input vector. Okay. It looks right to me. I don't know what to say. It's I don't know. I don't know why it would not be working. So let's try with a really small network just so that it goes fast. Linear, ReLU, linear, softmax. I guess these inner layers don't add that much. The main slowdown is from this. So almost 46% already just out of this. And then if I add a LayerNorm, after the or before the last linear and then softmax, which is where they put them in a transformer. Norm, linear, softmax, or norm, linear, softmax. This shouldn't hurt. It should actually help. So we should see at least 45% here. But we don't. So something's not working. I mean, ones and zeros make sense to me as the values of gamma and beta. Is that crazy wrong for some reason? LayerNorm initialization. Gamma beta. Ones and zeros, which makes sense. What else could it be? Wait, should I not be doing a square here? That looks wrong now that I look at it. NumPy variance. Or not NumPy, but like, yeah, show me this again. So variance is the sigma squared. So this shouldn't be squared. This should just be sigma. Or I should just call this var. Or just variance. It's not even... Okay, so that was a mistake. Hopefully that was the mistake preventing it from working. The sigma squared is the variance, but I was calling sigma the variance. Sigma is the standard deviation. Oh God, yes, that's beautiful to see. That means it's working good. Like that's better than it was without the layer norm. That was almost 48%. Okay, let's go back to having a big network. With a layer norm near the end. So if it's better than 45%, then it's helping, because we were getting about 45% without the layer norm. That's better than 45%. Very nice. And then just to confirm, without the layer norm, I might need a ReLU here without the layer norm. I'm not sure. It's too bad it takes like 30 seconds for each test. How long does it take? Almost a little over a minute, minute and a few seconds. Because I want to do one more test where I replace, okay, so 46.5 without the layer norm, 47.9 with the layer norm, so about 1.5% better. And if this were a ReLU instead, layer norm hard is accomplished. Good job, us. So we've got a lot of the pieces now. Let's take a look at what's left. Feed forward network is not what's left. We have that. So the yellows we have, the greens we have, the whites we have, the pluses we have. The things we're missing are the 3 attention blocks and all of this stuff at the beginning. Okay, 46. So adding a ReLU there actually hurt, if anything. So that's great. And then can we put a layer at norm at the beginning? Because that was, like in this diagram, they've got a norm at the beginning. In this diagram, they don't. So I don't actually know whether it's supposed to be helpful or not, but let's see. Let's just see. That's the beauty of doing it ourselves, is we can just figure it out. So the attention stuff is that, and that's the secret sauce as far as I understand for transformers. Like once they figured out attention, they figured out transformers. So I'm guessing this is going to be the hardest part, and I don't know how it works yet. The positional encoding stuff, I have no idea what that means. And embeddings / projections, I don't know what that means. I have an idea, but I don't really know what it means. And then the source and shifted target, I have no idea what it means. So I don't even know why there's 2 different columns in this transformer. I don't know what even like conceptually the difference between the 2 inputs are. So I think I'm gonna have to get some idea about what to do. Wow, that helped a lot, putting a layer at the start and the end. That was a big deal to get to 49 after a single epoch. That's really cool. Oh, I guess we can test whether saving the LayerNorm is working. So let's kill that. We'll just call this bad. It's not working because we need to save size. F. Because when we create it, we need to know a size. Which, well, actually, it doesn't matter. We can just say 0 because we're going to replace them immediately. So I should be able to load this now. Say hello. I hear we ristip. And if I scroll up, I hear we ristip. Good. Okay, so saving and loading works for our new layer. So that's really cool. I keep saying that, but with each thing that we add and it actually helps, it's kind of beautiful. Okay. So yeah, I have some homework to do to either learn about attention or learn about this stuff at the beginning here in order to figure out what we do next time, because I don't know, I would not know how to continue from right now. But that's going to be it for today. Hope this was helpful. Thanks for watching.